scientists want to know what is the role actually of this particular protein, and this is why they want to know whether how this protein arrangement changes over time. And so it's very, very difficult with an electron microscope to see distributions of proteins and protein arrangements. Why? Because in electron microscopy, there's no good contrast modality that allows you to label a certain type or species of proteins very, very specifically. In light microscopy, that's possible, because in light microscopy, you can attach a fluorescent molecule to the protein of interest. And then, of course, you don't see the protein of interest itself, but you see the fluorescent molecule. But since you know that this fluorescent molecule is attached to the protein of interest, you get a clue of where the protein of interest actually is, because you see actually its indicator, namely the fluorescent molecule. And as I said, this works extremely well in light microscopy through fluorescence labeling. And that's why light microscopy remained the by far most popular microscopy modality in the life sciences. So still nowadays, light microscopy is the most popular type of microscopy in the life sciences. But in general, it is limited by diffraction to about half the wavelength of light. But it was clear that due to its unique features, if it were possible to overcome the diffraction resolution barrier, to overcome this resolution limit, then of course it would make even a much, much bigger difference. And therefore, it was highly interesting to find out whether it's possible to cross this threshold, to cross this barrier, just as I'm showing you here. If that is possible, then such a new type of fluorescence microscope would make a substantial difference. So this is actually the topic that I worked on, but to be very honest with you, the reason why I looked into this problem, overcoming the barrier in light microscopy, was not so much the fact that I desperately wanted to do something to advance the life sciences. I did it, as you will see in a moment, out of curiosity. I wanted to know whether this works or not. Now, and as I said, I'm a physicist by training. So I want to know, is there a way to overcome this barrier, or is this barrier going to stand for the next 200 years as well? And in order to explain to you why I was eventually successful in overcoming the diffraction barrier, I'm explaining first the resolution problem. So why was the resolution of a light microscope fundamentally limited? Now, a normal microscope has the lens as its most important component, the objective lens. And the role of the objective lens is nothing but to concentrate light on a point. Now, nowadays, the light doesn't come out of a lamp as it used to be the case maybe 30 or 50 years back. It comes out of a laser. The laser light is focused by the lens into the sample. And let's assume the sample here consists of molecules, of individual molecules. So these black dots here are molecules. Now, if the lens could focus the light onto a single molecule, just like that, then you would have, of course, the spatial resolution that is at the molecular scale, because you could address the molecules here individually. You could, so to speak, detect them individually and separate it. But that's not possible. Why? Because the light, a laser light, propagates as a wave. And because light propagates as a wave, it's not possible to concentrate the light on a single point. What will happen as a result of this wave propagation is that you get a blob of light that is diffracted. Diffracted means that it's spread out, so to speak. It's not concentrated on a point. It has a diameter of at least 200 nanometers in this direction and about a micrometer, say 1,000 nanometers in the other direction. And because of that simple fact, it's not possible to address individual molecules here. It's not possible. What you will do is you will address all of them simultaneously, okay? Just like that. And because you address all of them simultaneously, many of them light up here, and each of them, of course, will scatter light back. So they will produce fluorescence back into the other direction. So So if you take a green light for illuminating the molecule, so yellow fluorescent light comes back, as you can see here with this yellow beam. And then, of course, this fluorescent light that goes back, each produces, from each molecule produces a blob of light here as well. The light is also a wave. When it goes back, it's also a blob. And then what will happen is that all the signal from all these molecules will overlap here in space. So each of the molecules that emits light here will produce such a blob. They will overlap in space. Then it will not be possible for a detector. Let's assume this here is a detector. Will not be possible for a detector to know which of these molecules has actually produced the signal in here, because the signal from each of these molecules overlaps here in space, and it's not possible for the detector to take apart the signal from the molecules. And this is why it's not possible to separate those molecules, because any of those molecules here in the focal region could have produced a photon that is detected in here. So no matter what detector you placed in here, it could be the eye, of course, or even a camera, there's no way to know if the photon that has been detected at a given point in time by the camera comes from this molecule or from that molecule or from that molecule or from that molecule. This is why it's not possible to take apart the signal from its molecules. Now, the person who realized that diffraction puts a limit to the resolution was this man, Ernst Abbe, who lived at the end of the 19th century in Germany. And he came up actually with an equation that describes this resolution limit. It's basically saying, in order to be separable, so distinguishable in the sample, two features have to be further away than the wavelengths, of light. This is this lambda, which is typically about 500, 600 nanometers, divided by this number, which is called a numerical aperture, but that's not so important. It's a number like 1, 2, 3, but not higher. And then you end up with this distance d. And that distance d, in the best case, is 200 nanometers. It won't get much smaller than that. And this is why people thought it will never, ever be possible to resolve better than about 200 nanometers. Now, this equation basically can be found in any textbook of optics, physics, you find it even in textbooks of molecular biology or cell biology, because light microscopy is very, very important to this field. And you can also find it on a memorial, which was erected in honor of Ernst Abbe in Jena in Germany, where he lived and worked. And there, basically, this equation, as you can see on this slide, is written in stone. And not only it was written in stone and in a textbook, it was also a fact. This is the end of it, and it was a fact. So at the time, I studied physics in the 1980s in Heidelberg, at that time West Germany. This was the end of resolution. One couldn't get better details than what you see in here. And it was clear that there was no way of getting any further. Now, I figured out that one can overcome this barrier. And so I developed a method that I will talk about in a couple of minutes, which is called STAT. And this was the first method that really showed you can overcome this barrier. It's not true that this limit here that is found here in this equation has to stand forever. At least for it's possible to overcome this resolution barrier, and there is viable physics, so to speak, or viable physical chemistry in this world that would allow you to get much, much sharper pictures. And these sharper pictures are seen in here. And so it was shown that this equation, or the limit set by this equation, can be fundamentally overcome. And as you can imagine, this led to special consequences. And one of the consequences it had for me is that I had the privilege of meeting Northern European kings, and the first king that I had the pleasure of meeting is Harald V of Norway. So he gave me and two other colleagues a prize, which is called the Kavli Prize. It's a very, very high recognition. I was very happy when I learned about it in 2014. And believe it or not, just a couple of weeks after I came back from Oslo with this nice smell, I got a phone call, and the phone call essentially said, okay, you will also have the pleasure of meeting his cousin. So Harald V's cousin, King Gustav of Sweden, in Stockholm in December 2014. And he also presented me with the medal. And afterwards, it was followed by a very, very nice banquet, and with very, very good food, I must say, and very, very nice company. And so it was really a highlight in my life. There's no doubt about it. And I could go on now talking about the gossip of this, but before doing that, or and you can ask questions, of course, afterwards, I will try to explain how it happened that I started to work in this field, and how did I come there, so to speak. Now, some of you may know it, but you may not know it, that I was not born in Germany. I was, as a matter of fact, born in a town called Arad. It's in Romania, western part of Romania, actually not that far away from Ukraine, as you will appreciate now on the map. And so it was, of course, during 1962, and that was during a communist time. I had also a German ethnic background, because my ancestors had come from Germany in the 18th century in that region. And now, since it was a communist country, it was definitely not a free country, and it was run by dictator Nicolae Ceausescu was his name. And I felt, okay, that's maybe not good to spend your life in such conditions. It's better to live in a free country. And so I convinced my parents at the age of 13, so if you have any chance, let's get out of the country and move to West Germany. And that was not so easy, but eventually we managed in 1978 to cross the Iron Curtain, which existed at that time, and move to West Germany. And we settled here in the southwest of Germany because we wanted to be far away from the Iron Curtain in 1978. And I liked that place. We didn't have any relations there. There was basically no one that we knew. But we had to start a new life there, and basically out of scratch, from nothing. And I liked it because I knew that it's very close to Heidelberg, which is a university town. And the good thing about West Germany, and still Germany at this time, is that that education is free. So this is a major asset, because if you have the opportunity to get educated, of course, you have the opportunity to set up your life the way you want, and eventually become very successful and earn your own money, of course, in a qualified job. And so after finishing high school, I went to Heidelberg and enrolled there as a physics student, and started to study physics. Now, in general, I was very much interested in doing very fundamental physics, like particle physics or theoretical physics and this type of stuff. But at the time, I had to make a decision on what to do for my PhD. This is what I looked like back then, believe it or not. Although I must say the glasses that I have in here are now very fashionable nowadays. At the time I had to make a decision, I kind of lost courage trying to do, say, theoretical physics, because the other students told me you should not do that, because if you do theoretical physics, you do something that is useless. No one cares for that. If you do that, you get unemployed. You don't get a job, and that was something that I definitely didn't want to do, because my parents still had to struggle here to set up their life in West Germany. So we were relatively poor, obviously. And then my father was very much worried that he would get unemployed, and eventually became unemployed. My mother became sick and later died on cancer. And I felt I should not do something that really is so exotic that I don't get a job, and in the end I cannot even support my parents if that is needed. And so I signed up with a professor who specialized in or had a company actually. So that was the attractive feature about him. He had set up a company as a, say, side project, more or less. He was a professor at university, but he also had a company. And in this company, they specialized on microscopy for all kinds of things, for measuring computer chips, for companies like IBM or Hitachi or Sony or this type of companies or Philips. And they also developed microscopes for biological imaging, for all kind of ophthalmoscopy, like scanning in the retina, and this type of stuff. And so I felt if I work actually with him for his company, then I would have a chance of getting a job afterwards. So I was very much motivated in working with him and with for the company, so to speak, doing my PhD actually, because then I would have a good chance of getting a job, maybe with Siemens or IBM or any of those companies. But you can imagine that if you, so what I did actually during those days, I got computer chips from Siemens. I was asked to inspect those computer chips, trying to measure the little tiny circuits and what are these the small line width that are that define the structure, to measure them to see if they are correct or not. Now imagine if you initially wanted to do something that is really groundbreaking in physics or so, like particle physics, relative physics, and then you end up with, you know, imaging or recording pictures from computer chips that are made by someone in a company like Siemens or so. There was a huge discrepancy, of course, because what I did actually for my PhD at that time, the level was so low actually from the scientific level that I felt, why did I study physics? And physics studies are of course very complicated and not so easy. Now I'm doing this kind of stuff that could be done by, and so I really became frustrated. At some point, I wanted to give up my thesis. I said, after 1.5 years, I still thought about just giving up everything and then maybe taking on another thesis work, or maybe just quitting or so. I was really frustrated. And then at some point I thought, okay, maybe I should still try to finish it to get my PhD, because after all, I spent so much time on it. Or maybe there is something else one could do with a light microscopy, which was, say, this old-fashioned 19th century physics. And then I realized the only thing that is left, in light microscopy that would be really cool is to break this resolution barrier, because everyone thinks this is not possible. If I manage to do that, of course, then this would be really fundamental. And this kind of lifted my spirits up, because I felt if I'm working on this subject and if I find a way to break the diffraction barrier, then so my job would be meaningful and I could do something really interesting and useful. And this would be really, really important. And then at some point, then I thought about it secretly, and then in the evening, I thought about, could that work, could that not work? But of course, everyone thought that this cannot work, because for fundamental reasons, this cannot work. And at some point, I became convinced that it could work. And the reason was, this diffraction barrier was found at the end of the 19th century, and more than 100 years had passed since this barrier was found. And so I felt so much physics was invented in the 20th century, the early 20th century, the mid 20th century. There must be something, of course, that that could be used perhaps to overcome the diffraction barrier. There must be a physical phenomenon that people didn't think of using for break-in diffraction barrier that exist already. So what I did is I scanned textbooks to find something that would get me beyond the diffraction barrier. So it was clear to me that it would be no new physics per se, no physical phenomenon, but existing physical phenomena could potentially be used to overcome the diffraction barrier if just one looks into the case again and with fresh eyes and with the goal of wanting to overcome the diffraction barrier. And this lifted up my spirits, and I said to my professor, let me work on this and please keep me in the lab for a while, and then I would look into this and there could be something. And he said, no, not really. It's not his field, and no. And the company, by the way, went bankrupt, and so he was not so much interested anymore. And I went to a lab in Heidelberg, a quite famous lab, European Molecular Biology Lab. I could work there for 1.5 years, 2 years, but again, it was not very much supported at that time. But I was lucky because I met a person who was Finnish, and he said, "Oh, why don't you come to Finland, to this place called Turku? We don't know if it works, of course, but if you find something, we give you some stipend and some time, and there is a small lab. You can try to work on it, and then maybe there is a way." And shortly, actually, then I went in '93 to Turku in Finland, and I left my girlfriend back in Heidelberg at that time, which was not so easy. But anyway, after about 8 weeks after I got there, I had the idea, and this was the first idea, of course, to overcome this resolution barrier in fluorescence microscopy. And that idea would, many years later, get me, 20 years later, would get me actually a Nobel Prize. And I'm explaining to you what this idea was that I had in those days. I was about 30 years old at that time. Okay, now you remember the problem. So there is this blob of light that makes many molecules fluoresce or glow, and as a result, here the signal is confused, and we cannot tell apart the signal from its molecules. That was clear. So it's not possible to make that green spot of light smaller. But being trained as a physicist, I knew not only you can use light to turn molecules on so that they fluoresce, but you can also use a blob of light such that you can turn fluorescent molecules off so that they don't fluoresce, provided that you use the right wavelengths. There is wavelengths of light. It's redshifted. So if it is green light, it has to be red light. It has to be the so-called emission spectrum of the dye that is just designed to turn molecules off. Now, turning all the molecules off here wouldn't make any sense, because then you would see nothing here, okay? But one can manage to kind of change the beam of light in such a way that it has a hole. And if it has a hole in here, then of course, the molecule here in the hole will not be turned off. That would still emit light. But those that are not in the hole, of course, they will be turned off. And then, of course, you turn those off, and then you have only this one on. And now, of course, the problem is, of course, virtually fixed, because only this one is emitting. It's as though we would have managed to concentrate the green excitation light just on this point. That's not what we did, actually, but in essence, the whole thing behaves as though only this one, of course, would be excited in the end and start emitting light. And then, since the signal from these molecules is all turned off, so look, this is all black. This chaos here in the back is gone. And then it's clear that the signal that is detected here, although it's blurred, sure it's blurred, is just from that molecule. And then we have sorted out the problem, because you see the signal only from this molecule. And then what do? We just need to scan it over the sample. And then, of course, we can get a picture of the whole thing. So I call this STAT. STAT stands actually for stimulated emission depletion. That's a technical term. it's because this phenomenon of turning off fluorescence with a red beam is called stimulated emission. That's a technical term. And that basically means that the light is taken away such that it can, a molecule cannot emit back into the detector. So I published this together with an intern at that time who visited me in Finland from Heidelberg in '94 as a theoretical proposal. Because, you know, I still was not a lab head or boss or something. I still, yeah, had a stipend in that lab, and I wanted to tell the world I have an idea, yeah, and it should work. So I published this idea as a theoretical proposal with numbers to show, at least on paper, that in theory this works, yeah, and it should also work in practice. The problem was that no one really believed in this. So this was really interesting in retrospect, that although there was a concept that sounded very logical and physically sound, community was not receptive. And it's very interesting. Actually applied for jobs in Europe, of course, in the United States. I wrote letters to all kind of places back in the 90s, hoping that I would get a job, but I couldn't. I even applied to technical schools, like not universities, like so, and they wouldn't take me. Anyway, it was a really difficult time, and I was a very poor guy. I didn't have much money, virtually almost nothing. Just the only thing I had was a car that had many dents and was about 20 years old. And I lived in a student dorm at that time, and I couldn't have invited you there. I was really a poor guy. But I must say at this point, in a way, I was not intellectually not dissatisfied, because I worked on a problem no one worked on, and I felt that I had an idea that no one else had, and it could be an important idea. Of course, at that time I've never thought that it would ever win a Nobel Prize or whatever. I mean, this was totally out of reach, because I couldn't even publish in highly visible journals. I couldn't publish in top journals. I was totally unknown. And so this is why I couldn't get a job. And I said, I applied at least to 30 places, but they wouldn't even invite me. They didn't take it seriously. But then after 4 years almost, I was very lucky. I happened to meet a person here at the Max Planck Institute in Göttingen, where I'm now, literally. And there was a director of the institute that was American by background, but he was director here in Germany. And he said, yeah, it may work, but it may not work, but at least it's interesting. Why not giving me a chance to try out whether it works or not? And that's why I came in '97. I came here, and I could set up a small group to work on the problem. And well, you certainly know the outcome. It turned out to work. Initially, I actually applied for money to get it, but then the German science funding body, they rejected the money first. But then I appealed, I got the money. And so it was, even when I came here, it was not so easy, but eventually it worked. And now you see this is before and after. And then it turned out, yes, it works. And these are images of the so-called nuclear pore complex. You can very nicely see now, as a result of the high resolution 8-fold symmetry here of the nuclear pore complex. And before, yeah, with the standard resolution, you see nothing. And here you see this fundamental increase in spatial resolution. And I still like making this comparison, although literally this picture can be found in high school textbooks in the German-speaking world. So in Germany, in Austria or Switzerland, the German-speaking, in German language textbooks, you find this image, exactly this image that I'm showing you here as a textbook image for overcoming the resolution barrier. Now, I was the only one initially, as I said, so I was the first and for a long time, the only one. Then the idea spread to the US. in about 2005, and then there were American groups who came up with a version of, in principle, the same idea, but implemented slightly differently on a so-called single molecule basis. So not say molecules were not turned off in specific locations, but randomly in space, and then they were localized. And this was a gentleman who did it first, Eric Betzig. And then this led to a Nobel Prize that was shared by him, by myself, and by this gentleman, W. Myrna, who was the first to detect single molecules. And this is the official poster of the 2014 Nobel Prize in Chemistry. You may ask, why is it chemistry? This is a physics problem after all. Well, I don't know, maybe because it has implications in chemistry. And you see here on the poster this concept of stat microscopy that I explained to you, with the green beam for turning molecules on, the red beam for turning molecules off, and that region that is left. And the alternative method, which is called Palmer storm, yeah, that was demonstrated by this gentleman first, turns individual molecules on and off, and then localize these individual molecules and then reconstructs the image. Now, I have set up a company, and the reason why I'm showing you this is that if there is a technical advancement, I'm not advertising this to you, but if there is a technical advancement, then you always have an edge, and then you can create something that is commercially valuable. This is something that I want to convey. And so with my former students, we set up a company that is now disseminating these high resolution microscopes around the world, and they get better over time. Initially were that big, now they are that small. This is just to show you that if an idea is really groundbreaking, it also leads to commercial values, and then to further development, and eventually gets better and smaller and more effective. That's normal part of the evolution. Now, I showed you that there was a substantial gain in spatial resolution, and at a time the Nobel Prize was given, both these methods, yeah, both STAT and also this Palm storm, could gain resolution increase roughly by a factor of 10. And so you could get down from 200 nanometers down to 20 nanometers. But conceptually, it was clear that, at least in principle, one should be able to get down to 1 nanometer, to the size of a molecule itself. But, you know, factor of 10 means 200 to 20, but between 20 and 1, there's still factor of 20 or 10, or another order of magnitude, yeah? And so the question was, since at the time the prize was given, the resolution was still at about 20 nanometers, whether it's possible really to get down to the molecule size resolution, because the size of the first molecule is about a nanometer, roughly. And so the goal in my lab in the last 5, 6, 7 years was to really get down to that level. And so if you want to do that, then you have to understand what options you have. And I realized that each of the two methods that got a share of the Nobel Prize have a specific strengths. The Palm storm concept has a specific strengths that it works with single molecules, and the single molecules are the smallest entity that you can have. So this is the strength. The disadvantage here is you don't know where the molecules are or come from, actually. So this is a problem, so to speak. You have to find it out. Here, instead, the advantage is that you are always in control of the coordinate, yeah, because you always know where this donut is located and where this minimum of this red donut beam is located. So the question is, what if you combine the strengths of the two? Take the single molecules from here, from the Palm storm, and take the donut from the STAT. And then you have the strengths of both. And this is exactly what happened in this concept called min-flux. You see, in this concept, we take individual molecules, we turn on and off individual molecules. So these principles of turning on and off is still critical for getting a high spatial resolution. But we find out the position of the molecule just by trying to match the zero here of the excitation beam with the position of the molecule. And if we do that, then we know exactly where the molecule is. And this is why we call it min flux, because the minimum of the excitation beam, that which is a hole actually, is made coincide with the molecule, and then the molecule doesn't emit. So we actually minimize the flux of fluorescent photons to find it out. But to cut a long story short, because you're definitely not interested in all this detail, the combination of the two led to a higher spatial resolution. Now, these nuclear pore complexes that you see in here, and now if you look at them, we are basically down at the molecular level. So you can associate the scale about 50 nanometers. You can associate each of these dots with individual fluorophores. And then if you compare it with STAT, which won a share of the Nobel Prize, it's clearly this min flux is better by an order of magnitude. And we're down the resolution of 1 to 3 nanometers. And if you compare this with confocal, which is the standard resolution, so to speak, here that's even worse. Yeah. So here between the standard and STAT, there's a factor of 10, and from here is not a factor of 10. So the difference between the standard to the resolution that we can do now is 2 orders of magnitude. So it's a factor of 100. It means not only we have broken the diffraction barrier, but we have overcome the resolution limits by 100-fold, and we are down at the conceptual limits of what fluorescence microscopy can do, because you can never be better in resolution than the size of the molecule themselves. And that's what we've reached. So we are now down at the size of the fluorescent molecule. And so this is actually quite, in the end, quite interesting development, because now we have the option of really going from the diffraction limit resolution down to the molecular scale, and this is viable. And as I said, 30 years back, no one would have thought that this would be possible. I would say even 10 years back, people thought that a resolution like this here in the middle would be the end of it, but now we are down. And this shows that science takes turns that are not anticipated, and that yeah, if one does things that are really exciting and you like them, then you can make really big strides. There are some lessons that I learned, and that I would put up here as messages. So in general, consensus is not equating reality, or not always equating reality. So there can be consensus that might be true, but very often consensus and reality might be totally different things, because there can be consensus on something, but still it's not true. This is something that is true for our daily life, but it's definitely also true in science. There could be consensus on something that is not true. And if somebody challenges consensus, then that person can often be treated as an outcast. The challenging consensus is not always welcome. Why? Because you can imagine there were many groups at that time who did their normal microscopy, or said there's other important things and this is not going to work, and so didn't want it to work. So that's important. So if you do something in your life that is really challenging consensus, don't be surprised if you're not welcome. This is actually the normal reaction of most people. You're not welcome challenging consensus. And then finally, to say something more uplifting, breakthroughs are very much done by curiosity and by the wish to do something interesting rather than do something useful. So as I said in the beginning, of course, I knew that fluorescence microscopy would be useful, but that was not the reason why I did it. I want to know whether it works or not. And I wanted to make a breakthrough. I want to find out, can I do a breakthrough? Yeah. And that drove me actually, and not so much the wish to be useful. Because if you do something and just for the sake of something, yeah, of usefulness, then you're very often staying within the same paradigm and same framework of thinking. But if it just goes after something and do something unexpected, then you might stumble across something that is not really anticipated. So breakthroughs very often come out of curiosity. And then finally, breakthroughs very often lead to economic value, always lead to economic value. Maybe not immediately, but after a while, it's just a matter of fact that if something is a breakthrough, then it definitely also leads to economic value. And so this is my advice. If possible, do the things that you really like, that you're really passionate about. And if you're staying in science, and do something that you're passionate about, although it might be very hard at times, and I understand that, it may even lead to a Nobel Prize. Thank you very much.
Thank you very much. It was extremely informative and motivating. It was really important for us. Thank you for your support during this difficult time. Our participant has no questions, so thank you. Thank you.
Thank you.
Goodbye.
Goodbye.